Okay, class, now we're discussing the resting membrane potential. Remember, every living cell in the human body has a resting membrane potential. I say living because top skin cells are dead, as you should know now. Okay, what do cells need to have a resting membrane potential? I've identified 6 things. The cell membrane, a cell membrane with a transmembrane integral proteins. Okay, we already talked about that. These channels should remain open, leaky. We talked about that. The membrane, we haven't talked, should act as a resistor and capacitor. Resistor and capacitor. So we haven't talked about that. Let me just say what we're looking at. Resistor, and these are kind of physics terms, you could say, and capacitor. A constantly maintained unequal distribution of certain ions, where particular ions are not in equilibrium: sodium, potassium, chloride, and the large molecular anions. The large molecular anions must remain trapped inside the cell. Remember, okay, the large molecular anions are proteins made inside the cell on floating ribosomes. Remember, proteins made to be used inside the cell would be made on floating ribosomes. Proteins used outside the cell or in the cell membrane were made on fixed ribosomes on the rough ER, and it would go through the Golgi. So these were made inside the cell, and they have a net negative charge. They're too big to get out. The presence of an ATP-dependent sodium-potassium pump. That's this right here. The presence of a sodium-potassium pump that we'll talk about. Okay, let's examine some of the above factors. What is meant by a resistor? The membrane must resist the movement of the ions. The ions can leak through, but not at a rate as fast as they'd like to. Why? The membrane is offering some resistance to them. A resistor in charge physics is something that holds back a charge. Resistance can be measured in ohms. Okay, if you have ever used an iron, an electric iron, you plug it into the wall, electricity comes out. Electricity, if you don't know, is the movement of electrons. Electrons come out of the negative end of the plug, go into the iron, and you're converting electrical energy to mechanical. But as you turn the dial up to make the iron hotter, you increase the resistance. The electrons then have a harder road to try to go through that resistor, and they release a tremendous amount of heat. Remember, the universe tends towards a state of entropy, and the most entropic form of energy is heat. And so that's what a resistor is. Okay, so the membrane is offering some resistance. It is not allowing these ions just to fly through. Okay, even though they are using passive transport and going down their gradient. Okay. A capacitor holds a charge to the surface of surfaces. If you've ever seen the heart defibrillator, you have these 2 paddles. These paddles are holding a charge, and when you put them on the chest, they discharge that charge. So a capacitor holds a charge. Okay. All right. In this case, the cell membrane holds a charge close to its 2 surfaces, where the net charge on the outside is positive close to the surface. Net charge outside positive, and the net charge inside negative close to the surface. And listen to my word, close to the surface. Is the total net charge inside the cell negative and not just on the surface? What I'm saying is, if I add up all the positive and negative charges inside here, does it come to a negative? And no, the answer is no. The charges inside of here added up would come to a charge of 0. And that is what we call bulk electroneutrality. Now, this is not in your text, so you're going to have to work with me on this handout. Bulk electroneutrality. Everything would add up to 0. Okay, then how could you have a net negative? Everything adds to 0, and that's where we're going to get into the dragging effect a little later that I'll talk about again, which is not in the text. Okay, is the total net charge outside the cell positive? No, it's just at the surface. Again, this would add to 0, and again, we would be talking about the dragging effect, so you can read my document. Okay, what are the normal distributions of ions involved? Now, first of all, let's get some concept out of the way. Whenever you put a bracket around a chemical, that means the concentration of. Whenever you put a bracket around a chemical, that means the concentration of. So let's go further. Okay, you can read this. I'm going to paraphrase it for you to make it quicker. Sodium is an ion in higher concentration outside the cell than inside. Sodium, in other words, has a 145 millimole. Remember moles? This is millimole outside, and inside 12. So higher concentration outside than inside. Potassium is an ion that has higher concentration inside a cell than outside. See this 140 to 4. Chloride is an ion that has higher concentration outside the cell than inside. So chloride is higher concentration outside. The large molecular anions are totally trapped. So obviously their concentration inside would be higher than that outside. Okay. Now, you say, well, if they're trapped, how would you have any outside? Let's talk about that. Any large molecular anions outside a cell are there because of damage to the cell membrane, where it may have leaked out and then the membrane was repaired, or at least by neighboring cells that would have died and released their large molecular anions. So it's very few, and any that did get out there were not intended to be out there. Were not intended. Okay, let's go further. As a result of these unequal distributions, ion distributions, the cell has two gradients. The combined term is called an electrochemical gradient. This is very important. As a result of this unequal distribution of ions, these ions, the cell has two gradients. And the buzzword is called, the combined word is called the electrochemical gradient. What do we have? We have a concentration gradient, that's what they call the chemical gradient, and a charge gradient, that's what they call the electrical gradient. So we have an electrochemical gradient, a concentration gradient, and a charge gradient. This gradient, okay, let me put it like this. A gradient acts as a gradual change. A gradient acts as a gradual change. So let me kind of this gradient here, I don't know how I got that, is a gradual change. There we are. This gradient is a gradual change. Like if you open a bottle of perfume, the aroma is high near the bottle and gradually dissipates as you move further from the bottle. So this is a gradual change, whether it be in charge or concentration. Okay? So this gradient is a gradual change, and I'm going to put here, of both concentration and charge. So this gradient is a gradual change of both concentration and charge. Okay? This was a recently written document, so I'm editing, I guess you could say, along the way, but this kind of helps you see where I'm going with this. The chemical gradient is a diffusion gradient. It involves the differences in concentrations of ions from inside to outside and vice versa, outside to inside. Remember, atoms and molecules move from high concentration to low concentration in diffusion. The sodium, which is high outside, wishes to move into the cell. Potassium, which is high inside, wishes to move out. Now, this is by your concentration gradient. I haven't gotten to the charge gradient yet. Chloride here wishes to move into the cell. I don't know why I have outside. Outside. Okay. Into the cell. So your chloride wishes to move into the cell, and the large molecular ions wish to move outside the cell. Okay. Chloride again has a higher concentration outside the cell than inside. Okay. So chloride wishes to move into the cell. Okay. The charge gradient involves the aforementioned charge held tightly to the membrane, which was a net negative here and a net positive there. Okay? So let's just kind of look at this. You can read on it. Okay? Chloride So I'm going to start first. Potassium then, as far as charge, would like to stay in the cell. Why? Because potassium is positive and the inside is negative. So in terms of charge, potassium would like to stay more inside. Okay? The sodium, when it comes to charge, would like to move in, just like it did with the concentration, because sodium is positive and the inside is negative. Okay? So you see things in some cases change when we get to concentration. Okay? So the large molecular anions would like to move out. They can't because they're negative, inside is negative, like charges repel. So let's look at it again. We're saying sodium would like to move in by charge. Sodium would like to move in by concentration. Potassium would like to move out by concentration, but stay in by charge. Chloride would like to stay out when it comes to charge, because it's negative, the outside is positive, but when it comes to concentration, move in. And the large molecular anions would like to move out by both accounts. They're negative, this is negative. So if you look at it, the large molecular anions and sodium are the ones that are most at disequilibrium, because you want to move in by both accounts and you want to move out by both accounts. Okay? Now, we come next to this. Can all the mentioned ions move through the membrane with the same ease? Now, let's go back to this again. Where the outside of the membrane is close and so forth. As you know, unlike charges like to move towards one, so the positive outside charge would like to move towards the negative and vice versa. So we just broke them down independently. You can do that on your own. Chloride likes to move in by concentration, but stay out by charge. Start studying it. Sodium likes to move in by concentration and by charge. These are important concepts. So break it down looking at charges. I did it for everything in this video. Okay. Then we come to book electroneutrality. What is it? Your textbook does not mention this, but for me this is a major factor in understanding the resting membrane potential. If you add up all the positive and negative charges inside the cell, it's going to come to zero. If you add them all up on the outside, it's going to come to zero. Okay. If the charges on the inside and outside has come to zero, how does the outside of the membrane closed surface has net positive charge and the inside have a net negative charge? This is due to what we're going to call the dragging effect. Now you can read on it, but here's what's basically, so just kind of listen to me real quickly here. All right. We come back to the desires of movement. We come back to the desires of movement, and then we look at what can go through the membrane easy. Okay? So I'm going to start first with sodium. Sodium has a strong desire to move into the cell. Why? Number one, because its positive inside is negative, and number two, because it has a higher concentration outside than inside. Sodium wants to move in. Sodium then decides to move in to try to reach some state of equilibrium. Problem is, sodium can't move in because it would add an extra positive charge inside, which would violate book electroneutrality. So for it to move in, it needs to bring a negatively charged to come in also. That would be chloride. I tell you what we're going to do. We're going to start right here at this on the next video because I'm running out of a little time here. So we're going to start on the next one.